Welcome to Unit 11, which is all about vectors. This is Day 1, Fundamentals of Vectors. You may or may not have learned a little bit about vectors in your science class, but I'm hoping that by the end of this unit you'll learn a little more from this class as well. Learning targets 1 through 4, showing two vectors are equivalent, writing a vector in component form, calculating the magnitude of a vector, and using vector addition and scalar multiplication to calculate the component form of a vector. In order to introduce this topic properly, we're going to use a little video clip from Despicable Me, which is an excellent movie. If you haven't seen it yet, you should. Here we go.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh, yeah! Check out my new weapon. Piranha gun! Oh, yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. I'm doing a demonstration. Oh, ow! It's so difficult sometimes to get the line back inside of me.
Mr. Brew, Mr. Perkins, you see now.
Okay, now that we saw a lovely vector give us that introduction, let's move on to the actual definition. A vector is a directed line segment. So it is a segment that has both magnitude and direction, just like vector says. Oh yeah. It's used for things like force, velocity, and acceleration. Basically anything you can measure that has a specific direction. That's really what we're focusing on. So those vectors are really line segments, but they have a direction to go. So it is from one point to the other point. So for the vector PQ, which we have in this picture, P is the starting point, Q is the ending point, which is why we have an arrow that points toward Q, even though there's a point Q where it actually ends, to show the directionality of that line segment. Notice the notation for PQ looks similar to the notation that we had in geometry for rays. However, this vector has an end point because it is a segment and it will not continue in the one direction. Point P in the picture is the initial point, initial starting. Point Q is the terminal point, terminal meaning ending. The representation for our magnitude, which is also known as length, the magnitude of this vector, is using the absolute value symbol. Remember that absolute value symbol means the distance from 0 on a number line, so it really indicates distance to begin with. So we use the magnitude of our vector by using that absolute value symbol. Okay, the set of all of the directed line segments that are equal to PQ is the vector PQ. To be equal, the magnitude and the direction must be the same. So not only does it have to be the same length, but it has to be going in the exact same direction. So I have a point or a vector down here that has a given magnitude and a given direction. If I start copying this and moving it around wherever I want, because they still have the same direction and the same magnitude, all of these vectors would be considered equivalent. So two vectors are considered equal if their directed line segments are equal. Well, how do we figure out if they're actually equal or not? It actually has a little something to do with what you learned way back in algebra, dealing with slope and rise and run. So you've got two different points. You've got your initial point, you've got your terminal point. Your initial point we're going to call your initial point to your new point. You've got an x component and you've got a y component. You go horizontally one distance, you go vertically another. For the vectors to be the same, those x and y values need to be the same. They need to go the same horizontal distance and the same vertical distance. So we have our 2 points, our initial point x1, y1, and our terminal point, x2, y2. So to figure out how far it run the x value, you would do x2 minus x1. To figure out how far it rose your y value, you would do y2 minus y1. That'll find that distance. If you end up with those values being the same for any given vector, then the vectors would be considered equivalent. Okay, so example 1, let u be the vector represented by rs and v be the vector represented by op. Prove u and v are equivalent by showing that they represent the same vector. So let's start off with vector rs, which we're going to call our vector u. S is the terminal point because it's at the end of that sentence where that arrow is showing that it's going. So that's my x2, y2. That means my r is my x1, y1. So using our formula, we can come up with the formula for rs, which is our vector u, by doing x2 minus x1 and then y2 minus y1. Negative 1 minus negative 4 is going to leave you with plus a positive, which gets you to 3, and then 6 minus 2 gets you 4. Move on to vector OP, which is our vector V. P is now our terminal point, so we do P minus O. 3 minus 0, and then 4 minus 0. Subtract, you get 3, 4. Because these two vectors have the same x component and the same y component, they would be considered equivalent. So we have just proven that fact. Example 2, kind of more of the same, still trying to find rs and op. Starting with rs, we've got our u vector, which we're going to do x1 minus x2, s minus r, because s is your terminal point. Subtract, you're going to get 6, negative 4. You do op, your x for p minus x for o, y for p minus y for o. You're going to end up again with 6, negative 4. Because the two vectors have the same x component and the same y component, you're going to have equivalent vectors. Okay, that form that we've been showing is called component form. Components are parts to something. So that form is the x part and the y part, the components that make up the vector. And we find that by doing our x2 minus x1, y2 minus y1. So that was component form that we've been seeing. In order to find the magnitude from component form, we use the square root of v1 squared plus v2 squared, our x component squared plus our y component squared. Well, where did that come from? This is absolutely nothing new to you. In Unit 10, we used it all the time. We have our v1 as our x and our v2 as our y, and they meet at a right angle because of a horizontal and vertical line. What do we use to find the magnitude, which would be the hypotenuse? Nothing other than the lovely Pythagorean theorem. So we use the Pythagorean theorem. That magnitude squared would equal v1 squared plus v2 squared. Take the square root, you're going to get your distance. Because it's a distance, we're going to use just the positive square root. Okay, so the next example is find the component form and magnitude. So start off with component form. We're going to do q minus p. So it's going to get us negative 5 minus 3, and then 2 minus 4. Simplify that, it's going to get you negative 8, negative 2. That's our vector. To come up with the magnitude, we need to do the Pythagorean theorem. So we use the square root of negative 8 squared plus negative 2 squared and put it together. We get the square root of 68. 68, believe it or not, has a perfect square that goes in it, which is 4. So I can rewrite this as the square root of 4 times the square root of 17, which will simplify to 2 radical 17. You will be expected to simplify these magnitudes if they are able to simplify. So you have your component form, negative 8, negative 2, and your magnitude, 2 radical 17. Next example, we're still finding PQ, so we're going to do Q minus P. 2 minus 6 Negative 2 minus 1, which is going to get us negative 4, negative 3. Moving on to find our magnitude, we do the square root of negative 4 squared plus negative 3 squared. 16 plus 9 is 25. Square root of 25 is 5. So we have our component form and our magnitude of our vector. Okay, scalar comes up next, and this is a vocab word you may not have heard before, which is why we're taking a second to define it. It's a number that gets multiplied by a vector. It indicates magnitude or size. You can use it for basically anything you're trying to measure the size of. Okay, so think about, anything you could make twice as big or 3 times as big. Whatever that multiplier is that you're multiplying by is the scalar for that number. Okay, so we use scalars for vector addition and scalar multiplication. I've got two different vectors, u and v, with components u1, u2, and v1, v2. I'm going to talk about really quickly vector addition and scalar multiplication. Vector addition adds the x parts together and the y parts together. Okay, so it's x plus x, y plus y. You can think about this in two different visual representations. Tail to head, you start with your initial vector, let's call that u, and then you add on from the end of u whatever your v vector is. From your very start place to your very end place would represent the vector u plus v. So adding those on together shows you the actual distance of the two combined. Then for the parallelogram method, you draw both u and v from the same starting spot. Notice I'm trying to make this exactly the same as the first one. Forgive me if I'm slightly off. And then you turn it into a parallelogram, wherever that parallelogram meets and that far side connected back to your initial point is your u plus v. If you look at these two pictures, you should see that those distances are the same. So it does not matter whether we think about this as tail to head or that parallelogram method, it should end up with the same results. Okay, next is scalar multiplication. K is our scalar. Hopefully you're used to using K as a constant by now. We're doing K times the vector u. To do that, you got to kind of think about component form as an XY pair. You're going to distribute to those multiple terms. Distribute to the x, distribute to the y. So it's going to get you the multiplier of u and the u1 and the multiplier of u2. If I think about a basic vector u, if I tried to multiply that times 2, it would make it twice as tall and twice as wide. So twice the height of the original, twice the width of the original. That would represent 2u. Well, what happens if you multiply by a negative? Well, right now my u is going right and up. And so if I multiply by a negative, both the x and the y would turn into negatives, and it would now be going left and down. So let's say I multiply by negative 1/2. Negative 1/2 u would go in the opposite direction and have half the distance of the original. This final set of examples, we get 3 different vectors and we're asked to do some operations. U plus w comes first. So u is 1, 5. We're adding w, which is 4, negative 2. We add the x parts together, 1 plus 4. And we add the y parts together, 5 plus negative 2. That's going to simplify to 5, 3 as my final answer as my vector. 3 times v, we're going to do 3 times the vector v. Again, think about that kind of as 2 separate terms. So we're going to go 3 times negative 2, 3 times 3, to get a final vector of negative 6, 9. Number 7 is v minus w. Start off with your v, negative 2, and then subtract w. So negative 2 minus 4 for x minus x, 3 minus negative 2 for y minus y. And then we're going to put it together, negative 6, positive 5 as my final answer. This last example is about as complicated as they get. You're doing a multiplier and addition. Just like in order of operations, you still have to multiply first before you add. So we're going to distribute the 2 into the first v, and then we're going to distribute the 5 into the w. It's going to leave us negative 4, 6, plus 20, negative 10. And then to add the vectors together, we add the x components, and we add the y components. Negative 4 plus 20, 6 plus negative 10 is going to leave us a final answer of 16, negative 4. This is the last of the notes for today, and hopefully you feel comfortable